A lot of experiments recently arriving on the Cygnus cargo vehicle, which docked with the International Space Station back on Sunday. Yesterday, I got a chance to catch up with one of the principal investigators of one of the more unique experiments that was brought on board. So why don't we go ahead and take a listen to that now here on NASA TV. So the Cygnus resupply craft, responsible for bringing over 2,700 pounds of supplies up to the crew of Expedition 38. Among those supplies, dozens of new experiments being brought on board the International Space Station. Probably one of the most unique and one of the most interesting on board, is known as the Ants in Space. Joining me now, the principal investigator for the project from the Department of Biology at Stanford University, Professor Deborah M. Gordon. Professor, thanks so much for joining me today. I really appreciate it.
Thanks for having me.
Now, as a professor of biology at Stanford, I've come to understand you study what's known as the evolutionary ecology of collective behavior. Now, why is that, an important research field, and why are we studying ants in space to learn about it?
I study how systems work without any central control. So in an ant colony, nobody's in charge, nobody tells anybody what to do. And a lot of human-engineered systems are like that too. For example, the internet, or the problem that the ants are solving in space is a problem that we have to solve ourselves. And it's the problem of how to search collectively, how a group of individuals, they could be ants, they could be robots, can search a space as effectively as possible without any central control. So this experiment is about expandable search networks. It's about how ants can adjust the shape of their paths to search a space in the best possible way, adjusting their searching to the number of ants and the size of the space. It's the same problem that a group of robots have to solve if they enter a burning building and have to figure out where to go and whether there's anything going on, anything that needs to be fixed, anybody that needs to be rescued. And we'd like to be able to design a system, an algorithm for robots to do that with as little information as possible, because that's the cheapest way to do it. And that's a problem that ants have had 150 million years of evolution to come up with great solutions.
Okay, and so we obviously know a lot about the evolution of ants up until this point. So specifically for this experiment, what were your guys' thoughts going into this? What hypothesis were you working from?
Well, we know something about how ants on Earth organize their searching collectively. They adjust the shape of their paths so that when there are a few ants in a large space, they use very straight paths to cover a lot of ground. But when there are many ants in a small space, they can be more thorough, and each ant can take a much more convoluted path, turning round and round in order to cover more ground, because an ant searching thoroughly in one place can afford to do that because there'll be another ant nearby searching next door, and they can afford to do that when they're very crowded. So how do they know how crowded they are? How do they assess density? They use the rate at which they meet. But in microgravity, information about density isn't perfect. In microgravity, because the way that they walk around is influenced by the lack of gravity, by that very basic orientation that they get from gravity being missing, then the rate at which they meet won't correspond to density exactly. So the hypothesis that we're testing is how in microgravity with imperfect information do ants adjust their paths to density.
Okay, and this was literally one of the first things to come out of the Cygnus craft once it was docked, and NASA astronaut Rick Mastracchio was able to set it up on Monday and actually execute the experiment. Can you describe just what happened, or kind of what some of your early observations were from the experiment?
Yes. Well, the experiment consists of ants in a rectangular arena with two barriers. So they traveled confined in a very narrow nest area, and then Rick put the barrier down so that there were a lot of ants searching a small area, and you'd expect them to use very convoluted paths because they can afford to be thorough when they're crowded. And then the second barrier went down, so then they were in a larger space. So suddenly density has gone down. It's as though there are a few ants in a big area, and they have to stretch out the network of paths. They have to use straighter paths. And so the experiment consisted of seeing how the ants would adjust their paths when their density changed. And it looks as though they had a little trouble in microgravity. The arena was very shallow, the ceiling was very low, so they weren't floating around, but still they had to work harder to move, and so their interactions with each other were influenced by that. And so we're going to be now analyzing the data to see how exactly they used the rate of interaction to adjust their searching.
Okay, and another thing that struck me is pretty cool about this study is you guys are also going to be kind of reaching out to classrooms and students to do their own versions of this experiment. Can you talk a little bit about that?
This is a really simple experiment that anyone can do, and with very simple, cheap materials, anybody can test how their local favorite ants are searching collectively, how they're working together to cover ground and be effective searchers. And I think that probably the invasive species that we tend to see in our kitchens all around the world are there because, for one thing, they're really good at searching. And so I think it'll be really interesting if kids around the world try this experiment with different kinds of ants, and then we're going to have a central database, compare the results, and see how ants in different places operate as searchers. So it's interesting to see not just how they do it in gravity and microgravity, but how they do it in different kinds of ecological conditions in different places.
And I mean, that definitely sounds I mean, what kids don't like playing with bugs? So it could definitely be a really cool way to get young kids interested in math and science. So obvious next steps for your research are going to be analyzing the data. Do you have any further outlooking plans, flying more ants, any other type of insect that might work with that swarm mentality?
I've learned in the course of talking to people about this experiment that there are a lot of really interesting biological changes that go on in microgravity. For example, the way that nutrients circulate around cells, the way that genes are expressed. And so I think that we really have a lot to learn about how collective behavior operates by trying it in space. So if I'm invited again to design more research, I would definitely say yes.
Would you be using ants again, you think? They seem to have quite a bit of evolutionary history behind them.
Yes, there's ants. Well, ants have evolved collective behavior, what we call in robotics distributed algorithms, for accomplishing a lot of different tasks. And I think that we really have a lot to learn from the ants.
Well, in the words of a famous TV newsman, I, for one, welcome our new insect overlords. Well, I mean, again, fascinating study. I really appreciate you taking some time out to give us the nuts and bolts of this, and we really look forward to seeing your results. Again, Principal Investigator for Ants in Space, Professor Deborah M. Gordon from Stanford University. Thank you so much for calling in.
Thanks very much.